And now in this lecture we'll answer two questions. In the first question, we find out the area of this green shape that is inside square ABCD. And in the second question, we find out the area of this green shape that is inside quarter circle AOB. So we'll start with the first question. In the drawing, we have square ABCD. This is angle PQC, that is right angle. This is line segment PQ, that is equal to 2 units in its length. This is line segment QC, that is equal to 4 units in its length. Our mission is to find out the area of this green shape. So first of all, we know that all the angles inside a square are right angles. So those four angles are all right angles. So what we know, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In addition, you know that all the sides of a square are equal to each other. So we define the length of one side of this square ABCD as A, and therefore all the other three sides must be also equal to A. So AD, side AD of square ABCD equals to A units in its length according to our definition. This is side AB. This is also equals to A units in its length. Side BC equals to A units in its length, and side BC of this square ABCD equals to A units in its length according to our definition. We define this line segment QB as X. So what is the length of the missing line segment AQ? From drawing it is very easy to see that AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So total AQ equals to A minus X units in its length. In the next step, we define this angle QCB as alpha. So in the right angle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this firmness angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at this point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is equal to 90 degrees minus alpha. This is a right angle plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to all three. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q according to all three. So in the right angle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, I will copy this right triangle APQ and this right triangle QBC in your page, and we prove that those two right triangles are similar to each other according to angle similarity rule. actually those are the two right triangles APQ and QBC that are going to the original domain. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So actually this is angle AQP. The right triangle APQ, and it is equal to this angle, this is actually angle QCB. The right triangle QBC. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle QAP. The right triangle APQ, and it is equal to this angle, this is actually angle QBC, in the right triangle QBC. So they are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha, therefore they are equal to each other. So actually, this is angle APQ. And the right triangle APQ, and it is equal to this angle, this is actually angle BQC. In the right triangle QBC, they are both equal to 90 degrees on alpha, therefore they are equal to each other. So we actually proved that all the triangles in this right triangle APQ are correspondingly equal to all the triangles in this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rules. So I write it down. I shall find out that this entire APQ is similar, this is the sum of similar to the right triangle QBC according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP in this right triangle APQ for side QB in this right triangle QBC is equal to side AQ in this right triangle APQ over side BC in this right triangle QBC, and it is also equal to side PQ in this right triangle APQ over side QC in this right triangle QBC. Okay, again, actually found out that side AP in the right triangle APQ over side QB in the right triangle QBC is equal to side AQ in the right triangle APQ over side BC in the right triangle QBC, and it is also equal to side PQ in the right triangle APQ over side QC in the right triangle QBC. AP is the missing side, so we leave it as it is. Over QB. QB is X, and it is equal to AQ. AQ is A minus X over BC. BC is A. And it is also equals to PQ, that is 2, over QC, that is 3. So total I can find out that according to equation 1, AP over x equals to a minus x over a equals to 2/3. So here, those two expressions are equal to each other, so we get equation 1 from those two expressions that are equal to each other. That is to say, according to equation 1, AP over x equals to 2/3. So you know, according to equation 1, AP over x equals to 2/3. So here we multiply this equation 1 by x, and finally we get that according to equation 1, AP equals to 2/3 x. According to equation 1, AP equals to 2/3 x. Those two expressions are also equal to each other, so we get equation 2 from those two expressions that are equal to each other. So actually, according to equation 2, a minus x over a equals to 2/3. So here we first multiply this equation 2, and finally we get that according to equation 2, so according to equation 2, 3 times a minus x equals to 2a. We open the brackets on this side of this equation 2, and you get that 3a minus 3x equals to 2a. Here we subtract 2a from this equation 2, and finally you get that according to this equation 2, 3a minus 2a is a, so a minus 3x equals to 0. Here we add 3x to this equation 2, and finally you get that according to this equation 2, a equals to 3x. A equals to 3x according to equation 2. In the next step, I copy this right triangle QBC in a new page, and we implement the Pythagoras theorem of this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evaluation for Pythagoras theorem. So actually this is the right triangle QBC that I quote from the original domain. In this right triangle QBC, according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. So I write it down. This will be equation 3. So actually, QC squared, that is the square of the hypotenuse, is equal to qb square plus bc square. The hypotenuse QC equals to 3, therefore QC squared is 3 squared, that is 9. And it is equal to QB square. QB is x, therefore QB square is x square plus BC square. BC is 8, therefore BC square is 8 square. So in total, according to equation 3, found out that 9 equals to x square plus 8. 9 equals to x square plus a square. This is according to equation 3, and according to equation 2, we have already found out that a equals to 3x. A equals to 3x, so if a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation in equation 3 by 3x squared from this equation in equation 2. We do it now and we get that according to equation 3, 9 equals to x squared plus a squared. A squared is 3x squared according to equation 2. So total, according to equation 3, I shall found out that 9 equals to x squared plus 3x squared. So, according to equation 3, equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, according to equation 3, we shall find out that 9 equals to x squared plus 9x squared. So 9 equals to x squared plus 9x squared is 10x squared. So according to equation 3, we shall find out that 9 equals to 10x squared. Here we divide this equation 3 by 10. And find again that according to equation 3, x squared equals to 9/10. So here we take out this equation and find again that according to equation 3, x equals to the square root of 9, that is 3, or the square root of 10 units in its length. So according to equation 3, x equals to 3, or the square root of 10 units in its length. But according to equation 2, we already found out that a equals to 3x, so a equals to 3 times x, and x is 3 over the square root of 10, so in total a equals to 3 times 3, that is 9 over the square root of 10. So we found out that according to equation 2, a equals to 9 over the square root of 10 units in its length. So actually, this is side DC, that equals to A, and A equals to 9 for the square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. AP equals to 2/3 x. So AP equals to 2/3 x, and x is 3 over the square root of 10. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So total AP equals to 2 over the square root of 10 units in its length. AP equals to 2 over the square root of 10 units in its length. So actually, this is line segment AP, that is equal to 2 over the square root of 10 units in its length. What is the length of 9 say with PD, from the drawing it is very easy to see that PD equals to AD minus AP. So it is known PD equals to AD minus AP. PD equals to AD minus AP. So PD equals to AD is A, minus AP. AP is 2 over square root of 10. So in total, PD equals to A minus 2 over square root of 10. So actually, PD equals to A, and A is 9 over square root of 10. So it is A minus 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10, that is 7 over square root of 10 units in its length. PD equals to 7 over square root of 10 units in its length. This is not 7 PD, it is equal to 7 over square root of 10 units in its length. In the next step, we will join points P and C together by a straight line. By joining points P and C, we can do two right triangles, the right triangle PGC and this right triangle PQC. It is very easy to see from the drawing that the green shape consists of those two right triangles. And therefore, the area of this green shape must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle PDC plus the area of this right triangle PQC. So write it down. The area of the green shape is equal to the area of this right triangle PDC plus the area of this right triangle PQC. And the area of the green shape equals to the area of the right triangle PDC plus the area of the right triangle PQC. So what is the area of the right triangle PDC? The area of this right triangle PDC equals to the base of the triangle that is PQ times the height that is QC over 2. So it is PQ times QC over 2 plus the area of this right triangle. So actually, this is the area of the right triangle PQC. So it is the base that is PQ times the height that is QC over 2. So what is the area of this right triangle PDC? It is the base that is PD times the height that is DC over 2. So in total, the area of the right triangle PDC is PD times DC over 2 plus the area of the right triangle PQC that is PQ times QC over 2. PQ is 2 times QC is 3 divided by 2 plus PD is 7 over square root of 10 times DC, that is 9 over square root of 10 divided by 2. So total we found out that the area of the green shape equals to area of time 2 times 3 over 2. 2 over 2 is 1, so we have to only be 3 plus, what is the value of this expression? 7 times 9 is 63, root of 10 times root of 10 is 10 divided by 2. So in total, the Lagrange shape equals to 3 plus 63 over 10 over 2 is 63 over 10 times 2. So in total, the Lagrange shape equals to 3 plus 63 over 10 times 2 is 63 over 20. So here we multiply 3 by 20 and then we divide it by 20 in order to come factor with this number, and we get that in the numerator we have 63 plus 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. 123 over 20 is 6.15 square units. So if we found out that the area of this green shape is equal to either 123 over 20 square units, or in terms of numbers, the area of this green shape is equal to 6.15 square units. So we finish with the first question, and the next step we present you the second question, and we will solve the second question in this lecture. Our mission in this second question is to find out the area of this green shape. So in the moment we have quarter second AOB, we know that side OB equals to 5 units in its length, and this is to say the radius of this circle and the radius of this quarter second AOB is equal to 5. In addition, we know that those three angles are all right angles, and we also know that arc AP equals to arc PQ equals to arc QB. So in the first step, we join points O and P together by straight line. And we join points O and Q together by straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement here rule 20. So I repeat rule 20. According to rule 20, in front of equal arcs in the circle, there are equal central angles. So in the moment we have a circle, and we know that this is arc AB, that is equal to arc CD in its length. So according to this rule 20, we have in front of this arc AB the central angle alpha. In front of this arc CD, we have the central angle beta. And according to this rule 20, because of the fact that those two central angles alpha and beta are located in front of those two equal arcs, they must be also equal to each other. That is to say, central angle alpha equals to central angle beta. So we can actually implement rule 20 in our drawing. And put in our drawing, we have arc AP that is equal to arc PQ, and it is equal also to arc QB. So in front of this arc AP, we have central angle AOP. This is central angle AOP. In front of this arc PQ, we have this central angle POQ. And in front of this arc QB, we have this central angle QOB. And because of the fact that those three central angles AOP, POQ, and QOB, they are all located in front of those three equal arcs AP, PQ, and QB, they must be also equal to each other. That is to say, if the size of this central angle AOP is x, then the size of this central angle POQ must be also equal to x, and the size of this central angle QOB must be also equal to x degrees in its side. So x plus x plus x, from the norm it is very easy to see that x plus x plus x equals to angle AOB. So write it down. x plus x plus x, that is 3x, is equal to the big angle AOB. From one side, but from the other side, it is given as the equation that the side of angle AOB is 90 degrees. Actually, AOB is a quarter circle, and therefore this angle AOB must be equal to 90 degrees inside. So, and for this equation, 3x equals to angle AOB equals to 90 degrees, we derive that 3x equals to 90 degrees. So here we divide this equation by 3, and finally get that x equals to 90 degrees over 3 is x equals to 30 degrees. So if you found out that center angle AOP that is equal to x equals to 30 degrees in size, this is center angle POQ that is also equals to x, and x equals to 30 degrees. And finally, center angle QOB that is also equals to x is equal to 30 degrees in its size. So, in the right triangle MOP, this angle equals to 90 degrees, this angle equals to 30 degrees, and therefore this third missing angle must be equal to 60 degrees in its size. According to the rule, it said that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in this right triangle NOQ, this angle equals to 90 degrees, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the same rule. OP equals to OQ, the above the radii of the circle, then is equal to 5, and therefore they are equal to each other. So OP equals to the radius R, that is 5. OQ also equals to the radius R, that is 5, according to what is given in the question. So in the next step, I copy this right triangle MOP, this triangle NOQ in the new page, and we prove that those two right triangles can point to each other according to angle side and angle rule. Simply, those are the two right triangles that I got from the original drawing. This is the right triangle MOP, and this is the right triangle MQO. So why those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees and therefore they are equal to each other. So here this is again MOP, and the right triangle MOP. And it is equal to this angle, that is actually angle MQO. In the right triangle MQO. They are both equal to 30 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. So here, this is again MPO. In the right triangle MOP, and it is equal to this angle, that is actually angle NOQ. In the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. And finally, side PO in this right triangle MOP is equal to side QO in the right triangle NQO. They are both together on the second, it is equal to 5 and therefore they are equal to each other. So PO equals to QO equals to the radius of the circle is equal to 5. So actually prove that those two angles and the side that is included between those two angles is the side OP are correspondingly equal to those two angles, and the side that is included between those two angles is the side OQ in the right triangle NQO. Therefore, we shall prove that those two right triangles can go into each other according to angle side angle rules. So write it down. So here triangle MOP congruent, this is the side of congruent to the right triangle NQO. According to angle side angle rule. And for the fact that those two right triangles can go into each other, we derive that they are also the same areas. Why? Because any right triangles that can go into each other, they must have the same areas. This is to say the area of this right triangle MOP is equal to the area of this right triangle MQO. So write it down. So repeat again, I should find out that the area of the right triangle MOP is equal to the area of the right triangle NQO. From the drawing, it is very easy to see that the right triangle MPO consists of two components. It consists of this component for the other MN, we define this with this point S. So right triangle MOP consists of this green quadrilateral MNSP, and it will also consist this right triangle NOS. Therefore, the area of the right triangle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the green quadrilateral MNSP plus the area of this small right triangle NOS. So write it down. Right triangle MOP is equal to the area of the green quadrilateral MNSP plus the area of this right triangle NOS. Again, the area triangle MOP equals to the sum of the areas of the two components that is consist of. That is to say, is equals to the area of the right green quadrangle MNSP plus the area of the right triangle NOS. And according to equation 1, this equation 1, the area of the right triangle MOP is equal to the area of the right triangle MQO. So this is the right triangle NOQ. It's very easy to see from the drawing that this right triangle NQO consists of those two small triangles. That is to say, it consists of this right triangle NSO, and it also consists of this triangle OSQ. Therefore, the area of this right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this triangle SOQ. So I write it down. Again, the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right small triangle NSO plus the area of the triangle OSQ. So this is equation 1. So in this equation 1, we have the area of triangle NSO on both sides of the equation, so we subtract the area of triangle NSO from this equation 1, and we get that so the area of triangle NSO will get cancelled, and we left only if the area of quadrangle MNSP is equal to the area of triangle OSQ. So actually found out that the area of this green quadrangle MNSP is equal to the area of this white triangle OSQ. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the green quadrangle MNSP plus the area of this green small shape PSQ. So I write it down. The area of the green shape in total is equal to the area of the green quadrangle MNSP plus the area of this small green shape PQS. Again, we should find out that the area of this green shape in total is equal to the area of the green quadrangle MNSP plus the area of the small shape PQS. But we already found out that according to this equation 1, the area of quadrangle MNSP equals to the area of triangle OSQ, therefore can substitute the area of triangle of quadrilateral MNSP by the area of triangle OSQ because they are equal to each other. We do it now, and we get that the area of the green shape in total is equal to the area of quadrilateral MNSP is equal to the area of triangle OSQ, so we substitute the area of quadrilateral MNSP by the area of triangle OSQ plus the area of the small shape PQS. So in total we shall find out that the area of this green shape equals to the area of this triangle SOQ plus the area of this small shape PQS. But the area of the small shape PQS plus the area of this triangle SOQ is equal exactly to the area of sector POQ. Again, the area of the small shape PSQ plus the area of this triangle SOQ is equal to exactly to the area of sector POQ. So write it down. The area of triangle OSQ plus the area of the small shape PQS equals exactly to the area of sector PQO. So here the rounded line above PQO is the sign for a sector, it means the area of sector PQO. So in total we shall find out that the area of the green shape equals to the area of sector PQO. But what is the area of sector PQO? The area of this sector PQO is equal to pi r squared, that is the circle that contains this sector POQ times the angle between the legs of the sector that is 30 degrees over 360 degrees. So now write it down. The area of sector PQO equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. The radius of the quarter circle, that is also the radius of the circle that contains the sector, r equals to 5 according to what is given in the question. If r equals to 5, it means that r squared equals to 5 squared, that is 25. So pi r squared is 25 pi times 30 degrees over 360 degrees. 30 degrees over 360 degrees is 1 over 12. And 25 pi over 12 is 6.545 square units. And that is the answer to the question. Repeat again, we can find out that the area of this green shape is equal to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape is equal to 6.545 square units. So finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this green shape. So, in the moment, we have square ABCD. This is angle PQC, that is the right angle. This is 97 PQ, that is equal to 2 units in its length. This is 97 QC, that is equal to 4 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we know that those four angles are all right angles because ABCD is a square. In addition, we know that all the sides of ABCD are equal to each other. So if you define one side of this square ABCD as A, then all the other sides must be also equal to A. So DC equals to CB equals to BA equals to AD equals to A according to our definition. We define this line segment QB as X. What is the length of the missing line segment AQ? AQ equals to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. We defined this angle QCB as alpha. So in the right angle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at this point Q, here the sum of the angles must be equal to 180 degrees, according to rule 3 that states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have this side of AB at point Q? We have this angle that is 90 degrees minus alpha, this angle that is 90 degrees, and therefore this first angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles on this side of the straight line AB at point Q according to rule 3. So in the right triangle, so this missing angle equals to alpha. In the right triangle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copy this right triangle AQP, this right triangle QBC in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So okay, those are the two right triangles that I proved from the original drawing. This is the right triangle APQ, and this is the right triangle QBC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the triangles in this right triangle APQ are correspondingly equal to all the triangles in this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP, this right triangle APQ, over side QB, this right triangle QBC is equal to side AQ in this right triangle APQ over side BC in this right triangle QBC, and it is also equal to side PQ in this right triangle APQ over side QC in this right triangle QBC. Again, I can find out that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. QB is X, AQ is A minus X, BC is A, PQ is 2, and QC is 3. So in total, according to equation 1, we actually found out that AP over X equals to A minus X over A equals to 2/3. Those two expressions are equal to each other, therefore we added equation 1 from those two expressions that are equal to each other. So according to equation 1, AP over X equals to 2/3. Here we multiply this equation 1 by X, and we found out that according to this equation 1, AP equals to 2/3 X. Those two expressions are also equal to each other, so we added equation 2 from those two expressions that are equal to each other. So according to equation 2, A minus X over A equals to 2/3. Here we first multiply this equation 2, and we found out that according to this equation 2, 3 times A minus X equals to 2A. Here we open the brackets on this side of this equation 2, and we found out that the 3A minus 3X equals to 2A. Here we subtract 2A from this equation 2, and we found out that 3A minus 2A is A, so A minus 3X equals to 0. Here we add 3X to this equation 2, and we found out that according to this equation 2, A equals to 3X. So here copied this right angle QBC in a new page and implemented the Pythagoras theorem in this right angle QBC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, this is the right angle QBC, this is coming from the original drawing, so according to the Pythagoras theorem, in this right angle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So according to equation 3, I can find out that 9 equals to x squared plus a squared. This is according to equation 3, but according to equation 2, we have already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation, equation 3, by 3x squared. From this equation, equation 2, we did it, and we have found out that 9 equals to x squared, and a squared is 3x squared according to equation 2. So in total, according to equation 3, I have found out that 9 equals to x squared plus 3x squared. So 9 equals to x squared, and 3x squared is 9x squared. So in total, I actually found out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared. So 9 equals to 10x squared. Here we divided this equation 3 by 10, and finally found out that x squared equals to 9 tenths. Here we took out all of this equation 3, and finally found out that according to this equation 3, x equals to the square root of 9, that is 3, over square root of 10 units in its length. Or x equals to 3 over square root of 10 units. So according to equation 2, a equals to 3x. So a equals to 3, and x is 3 over square root of 10. So a equals to 3 times 3 is 9 over square root of 10. So in total, we have found out that a equals to 9 over square root of 10 units in its length. So this is side DC, that is equal to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. So AP equals to 2/3, and x is 3 over square root of 10. We have 3 in the numerator and 3 in the denominator, so 3 will cancel, and we have only 2 over square root of 10. So in total, we have found out that AP equals to 2 over square root of 10 units in its length. This is side AP. Line segment AP, that is equals to 2 over square root of 10 units in its length. What is the length of PD? From the drawing, it is very easy to see that PD equals to AD minus AP. And again, PD equals to AD minus AP. So PD equals to AD, that is A, minus PD, that is 2 over square root of 10. So PD equals to A minus 2 over square root of 10. A is 9 over square root of 10 units, so therefore PD equals to A, that is 9 over square root of 10 units, minus 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10. So in total, we found out that PD equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by straight line. By joining points P and C, we can get here 2 right angles. This is the right angle PGC, and this is the right angle PQC. From the drawing, it is very easy to see that the green shape consists of those 2 right angles. And therefore, the area of this green shape must be equal to the area of the sum of the areas of the 2 components that it consists of. That is to say, the area of the green shape in total must be equal to the area of this green right angle PGC plus the area of this green right angle PQC. So again, the area of the green shape in total equals to the area of the right angle PDC plus the area of the right angle PQC. The area of the right angle PDC equals to the base PD times the height, that is DC over 2, plus the area of the right angle PQC, that is the base PQ times the height, that is QC over 2. So the area of the right angle PDC is PQ, PD times DC over 2, and the area of the right angle PQC equals to PQ times QC over 2. PQ is 2, QC is 3, divided by 2. PD is 7 over square root of 10, PC is 8, and A is 9 over square root of 10, divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 we can cancel, and we left only 3. What is the value of this expression? 7 times 9 is 63, square root of 10 times square root of 10 is 10, divided by 2. So there the ratio equals to 3 plus 63 over 10 over 2 equals to 63 over 10 times 2. So it is 3 plus 63 over 10 times 2, that is 20. So in total there the ratio equals to 3 plus 63 over 20. Here we multiply 3 by 20 and then we divide it by 20 in order to come out of this number. So in total, in the numerator we have 63 plus 3 times 20, that is 60, divided by 20. 63 plus 60 is 123, divided by 20, that is 6.15. So in total, we should find out that the of this ratio equals to either 123 over 20 square units, so there are some numbers there of this ratio equals to 6.15 square units. We finish with the first question. In the next step, we're going to do the second question and solve the second question of this lecture. In the second question, our mission is to find out the area of this green shape. So, in the domain we have quarter circle AOB. We know that OB equals to 5, that is to say the radius of this quarter circle equals to 5. In addition, we know that those three angles are all right angles. And we also know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So, in the first step, we join points O and P together by a straight line, and we join points O and Q together by a straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement the rule 20. So, I can click on rule 20. According to rule 20, in front of equal arcs in the circle, there are equal central angles. In the domain, we have a circle, and we have here arc AB that is equal to arc CD. In front of arc AB, we have central angle alpha. In front of arc CD, we have central angle beta. And because of the fact that those two central angles, alpha and beta, are located in front of those two equal arcs, they must be also equal to each other. That is to say, central angle alpha equals to central angle beta. So we can actually implement rule 20 in our drawing. Why? Because in our drawing, we have arc AP that is equal to arc PQ, that is equal to arc QB. In front of this arc AP, we have central angle AOP. In front of this arc PQ, we have this is central angle POQ. In front of this arc QB, we have central angle QOB. And because of the fact that those three central angles AOP, POQ, and QOB, they are all located in front of those two equal arcs AP, PQ, and QC, they must be also equal to each other. So if we define the size of this central angle AOP is x, then the size of this central angle POQ must be also equal to x, and the size of this central angle QOB must be also equal to x degrees in its size. It is very easy to see that from the knowing that x plus x plus x, in total it is equal to the big angle AOB. X plus x plus x is 3x, so 3x equals to angle AOB. From one side, from the other side, we know that AOB is a quarter circle, and therefore angle AOB equals to 90 degrees. So we can write here that angle AOB equals to 90 degrees. And from this equation, 3x equals to angle AOB equals to 90 degrees. We will derive that 3x equals to 90 degrees. Here we divided this equation by 3 and finally found out that the missing angle x equals to 90 degrees over 3 is 90 degrees over 3 is 30 degrees. So central angle AOP equals to 90 degrees, central angle POQ equals to 90 degrees, and central angle QOB is also equal to 30 degrees in its size. In the right angle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in the right angle NOQ, this angle equals to 90 degrees, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size, according to the same rule. OP equals to OQ. They are both the radii of the circle. That is equal to 5, and therefore they are equal to each other. So in the next step, we'll copy the right angle MOP and this right angle NOQ in a new page, and prove that those two right angles can go into each other according to angle side angle rule. Okay, those are the two right angles MOP and NQO that are going to the original drawing. So why those two right angles can go into each other? First of all, those two angles are both equal to 30 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. And finally, side OP equals to side OQ. They are both the radii of the circle and therefore they are equal to each other. So I shall prove that those two angles and the side included between those two angles, that is side OP, are correspondingly equal to those two angles, and the side included between those two angles, that is side OQ, in the right angle NQO. And therefore those two right angles can go into each other according to angle side angle rule. We have two angles and the side included between those two angles that are correspondingly equal to those two angles, and the side included between those two angles in this right angle NQO. And therefore those two right angles can go into each other according to angle side angle rule. And from the fact that those two right angles can go into each other, we derive that they have also the same areas. That is to say, the area of this right angle MOP is equal to the area of this right angle NQO. Repeat again. The area of triangle MOP is equal to the area of triangle NQO. From the drawing, it is very easy to see that the right angle MQO consists of this green quadrilateral MNSP, and it also consists of this right angle NOS. And therefore the area of this right angle MQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this green quadrilateral MNSP plus the area of this right angle NOS. So repeat again. The area of the right angle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of quadrilateral MNSP plus the area of the right small triangle NOS. And note that according to equation 1, the area of triangle MOP equals to the area of triangle NQO. This is the right triangle NQO. It is very easy to see from the drawing that this right triangle NQO consists of two small triangles. It consists of this right small triangle NSO, and it also consists this small triangle NOQ. And therefore the area of this triangle NOQ must be equal to the sum of the areas of the two components that it consists of. That is to say, the area of the right big triangle NQO must be equal to the area of the small right triangle NSO plus the area of this right triangle SOQ. So again, we shall find out that the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the small right triangle NSO plus the area of triangle OSQ. We have the area of triangle NSO on both sides of the equation, so we subtract the area of triangle NSO from this equation 1. So the area of triangle NSO we can cancel, and left only with the area of quadrilateral MNSP that is equal to the area of triangle OSQ. Our mission is to find out the area of this green shape. From the drawing, it is very easy to see that the area of the green shape equals to the area of this green quadrilateral MNSP plus the area of this green small shape PQS. Again, the area of the green shape in total equals to the area of quadrilateral MNSP plus the area of the small green shape PQS. But we have already found out that the area of quadrilateral MNSP equals to the area of triangle OSQ. Therefore, we can substitute the area of this quadrilateral MNSP by the area of triangle OSQ. We did it, and we found out that the area of the green shape in total equals to the area of triangle OSQ plus the area of the small shape PQS. So the area of the green shape in total equals to the area of this right triangle SOQ plus the area of this green shape PQS. But the sum of the areas of those two components is equal exactly to the area of sector POQ. And therefore, the area of the green shape in total equals to the area of sector P or Q. Okay, so the area of the green shape in total it is equal to the area of sector P or Q. What is the area of the sector P or Q? The area of sector P or Q equals to pi r squared, that is the area of the circle that contains this sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. Okay, again, the area of sector P or Q equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. R is 5, therefore r squared is 25 squared is 25, so in total pi r squared is 25 pi, and 30 degrees over 360 degrees is 1 over 12. So in total, this expression equals to 25 pi over 12. That is 6.545 square units. So in total, we found out that the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, thank you very much.